If you zoom in on a circle close enough, it looks like a collection of straight lines. So it's the same way here, that if you zoom in and you make the slices small enough, whether it looks like a circle or it looks like a rectangle, it's going to eventually just look like a regular ordinary shape. So now instead of having these really odd shapes, you're going to zoom in close enough here where if you slice this one really, really, really small, it'll just look like a regular straight line there. So that's what we're doing. We're just making those slices so small that the odd shape doesn't really make a difference. Yes?
The delta x has to happen on the side that's irregular, because that's where you want to approximate.
Exactly. So if you have your...
So we have to find a way to orient it so that the height is always the same, and the delta x is happening on that irregular side of the shape.
Exactly, because once you get that delta x and you slice it small enough, then those little irregularities won't make a difference. So like I said, it's kind of like the circle, where you get that circle and you zoom in close enough, it looks like a series of small straight lines. Same thing here. If you get in close enough on that one and you make those slices a little smaller, so instead of 5 slices, 10 slices, 20 slices, 50, 100,000, however many it is, those slices eventually start to give you a really exact shape. So now you can say, okay, I'll just take the volume of this little exact slice where now that I've made it small enough, instead of having that odd shape, I cut it so thin that it kind of looks like a square, or it kind of looks like a little bit of a circle. It looks like something I'm used to seeing. So that's what you want. You want to be able to get that one slice so thin that it actually makes sense. Because trying to get this one won't make any sense at all. Does that make, I hate to say sense again since I've used it so many times, but is that a little bit clearer? Okay. You good with that one?
Get to the bread of the
You
matter.
good? Okay. All right. Okay. So we know once again that our volume formula, once we go through everything else, kind of looks like this. Okay. But like I just mentioned, that's only if we have just a normal amount of slices. We want to increase the slices more and more and more and more and more. As the slices increase, we get closer and closer to the actual volume. Okay, because each slice looks a little more like a rectangle or a little more like whatever shape, depending on how odd it was to begin with. So again, that's depending on the original shape. Okay, so that means our volume is equal to, remember, we're going to get all those slices and we're going to add those slices together, and that's going to give us our volume. So you're going to get the sum of all those slices of but since we want those slices to get more and more and more and more and more, we're not going to be content with just a certain number. That means we want the number of slices to approach infinity. Okay? So that's going to give us our volume. If we add all of those slices together, even though each individual slice is a little piece of the volume, you add all those together, you get the total volume. Okay, does that make sense a little bit? All right. And if you recognize this, oh, thank you. It looks a lot like the definite integral formula, which means we can get this, and our volume will now equal from some a to b of a of x dx. So you're probably asking, well, I have to go through all of that to answer a question? No. You answer your question just by using that formula. Yes.
Are there any shapes that this is an exception? That there's an exception to this?
You have to have something that is consistent.
Yeah, it will
with
have to be
regular.
continuous. If it's not continuous, then you wouldn't be able to use it. All right, so it all goes down to this, and the reason I didn't just hand you the formula is because you would have to figure out what the cross-sectional area is first. So this a of x won't always be the same thing. So I'll give you a couple of examples of what it is. Yes?
So, when you said like continuous,
Mm-hmm.
let's say we have a shape that's like two cones together, so to speak,
Mhm.
but they're like, let's say they're like weirdly wobbled, so we can't just say the formula of two cones.
Mm-hmm.
As they converge, like an hourglass figure,
Mm-hmm.
would that become non-continuous where they meet? Like, would there not be an area function to dictate what that hourglass point is?
Well, in that case, you'd probably just use the
Definite integrals then?
the formula where, let's say, the integral from a to c of a of x dx. Remember, you can just break that down. So you can get the integral, the volume of the first cone,
It's not one.
and then, yep, and then just go from b to c. So from a to b, a of x dx plus from b to c,
Okay.
a of x dx. Okay, so really by continuous is one of those things where if your slices have, oh, I thought that one cut off, have like weren't all there. So if your building is there and instead of the volume it's, I'm trying to think, it's best way to figure it. I'm trying to think of something I can use as an example.
The inflection point is what's the problem.
Not really. Can't see where the inflection point would really bother that one.
It doesn't make it not continuous when there's a.
We could say non-continuous is like trying to measure the volume of this without taking into account this hole in the way. I guess.
Yeah, so it would kind of be one of those where there are openings in between there. So if you have you can get the volume of the room. So if you have the volume of this way, if you let's say if you have a missing window here, then that's going to affect the volume because it's not
But it's
continuous
like
and
the
closed.
absolute value function where there's an inflection point at the zero, so you can't differentiate it across the whole. That's why you have to take sections of the first.
Yeah, the section of the first second because
It's a piecewise function because of the inflection point between the two cones. That's what I'm saying. Just like the absolute value function. Because it's not differentiable.
Yeah, it's not differentiable because
At the
of
inflection.
that's
what I
true.
meant.
Yeah, okay, I see what you're saying. Yeah, you could do that, but with this one, that's about you couldn't just use the formula outright. But if you did have sections, so if you found the volume, let's say this window was missing, if you found the volume up to the window, then you find the volume in between it, it still wouldn't it would give you a close approximation, but because of the missing windows, you wouldn't have an accurate volume. So kind of depends on that.
Okay.
Does that make sense?
Yes.
All right. Okay. All right, so I don't really need this one. Okay, so let's say we get a quick example. Okay, so let's say if you have a cylinder shaped, and let's say that there, that there. Okay, so if you have a cylinder shaped building on an x-axis. that begins at x equals -2 and ends at x equals 4. Okay. Now, if you know if the radius is 3, ooh, bless you. What is the volume of the cylinder? Or of the cylindrical shape? And of course, we're going to use integration. Okay. Now, this one could be easily solved if you use the volume of a cylinder, which would be pi radius squared height. Cut that value in half. But we're just going to use integration just because. So.
Torture us.
Exactly. So, make something really, really simple and complicated. That's what math is. So. Okay. So, once again, we know that if we got that, because it's this way, if we sat it on its side, we know the area of that base, is 1/2 pi radius squared. Okay? Because we know it's half a cylinder. If we had a complete cylinder, the area of the base would be pi radius squared. But because it's half a cylinder, we get that area, cut it in half. Our cross-sectional area is 1/2 of the pi radius squared. Does that make sense? All right. Okay, so to find the volume, A to B, make sure that's up enough. Dx, that's the interval. We already know it's from -2 to 2. Pi radius squared dx. No, what?
Isn't it a 4, not 2?
Is it 4?
Yeah, it's 4.
Yep, it's 4. Sorry about that. Okay. So that means that we already know our radius is 3. So we would replace that now if we wanted to.
Don't we have to divide by Marston?
Hmm?
For the
Did I leave out the half? Yep, I did leave out the half. Sorry about that. I'll just, that should be. Sorry, I left out the half there. So 1/2 radius squared, pi radius squared. Okay, so that means from -2 to 4, let me rewrite it, make sure it's a little clearer. And instead of the radius squared, we just put in 3 squared. Okay, so that gives us, was that 9 pi over 2, which we can factor out of there. -2 to 4 dx. Which you could just say the integral of 1. Yes.
How can you integrate with respect to, you're using dx, right?
Mm-hmm.
But you don't have an x variable in your integral. So
Mhm.
how do you know what to integrate with respect to?
Oh, because we-
Is the-
Hmm?
Never mind.
Oh. Well, with that one, it was actually given to you in the question. That was the one.
What is it?
When they tell you that it begins at x equals -2.
Those are the bounds though.
Yeah, that's where you integrate with respect to x. That's where your slices are going along the x-axis.
I'm saying when you write the equation with respect to dx, there should be an actual
Yeah,
x in
you have-
there.
It
There
has to be
doesn't
an
have
x
to be.
Nope.
variable.
It doesn't have to be.
Same way x is the power of 0, still x value, just not necessarily. Yeah, just nothing there. So even if it's a constant, it could be a function of x. Okay, which in this case is how it came about. So the integral of
So what's
really,
the function?
hmm?
So what's the function?
Oh, once you integrate 1 with the power, well, 1 with respect to x, you end up with 9 pi over 2, exactly, x.
Integrated that formula.
Yep, from -2 to 4. Yep. So even if there's no function there, still a function. Still a function there. All right. So we know, using the fundamental theorem of calculus. Oh, there you go. Sorry about that. Okay, you plug in your 4 minus your -2. Okay, which is 9 pi over 2 times 6, which is 27 pi. Okay, so that's your approximate. Of course, pi is irrational, so you won't have an exact value, but that's your value there. And again, if you decided to go the short way, volume equals 1/2. Can you see that? Yep, make sure move that up a little bit. Pi radius squared height, if you just went the regular ordinary volume, you notice that's 1/2 times pi times radius squared times the height. Remember, from -2 to 4 is a distance of 6. So that would give you your 6. Okay, so 6 times 9 gives us our 54. 54 divided by 2 is 27 pi. So there's an easier way to get it, but this was the using integration steps to get it. Okay. Any questions on that one? All right. Okay, make sure I put this in the right spot. Yep. All right, so let's do one more example. Okay, so let's say, suppose you have a dome. Circular cross sections. With the outline y equals plus or minus square root 45 divided by 2, 90 minus x. So that's pretty much the shape for the interval 0 to 90. And we're going to measure that in feet. Okay, so this graph will look something like this. Kind of like a sideways parabola. Okay, so,
Do you mind sliding that up just a tiny bit so I can see the top?
oh, sorry about that. So it would kind of look like that. Okay, remember x is from 0 to 90. And if you calculate, you know, your y value goes from -45 to 45. All right. So you want to find the volume of the dome. Okay. Okay. Now with this one, the first thing you want to do is figure out what your radius is. Okay. Now your radius is going to be the distance from the x-axis to the curve, which kind of varies as it goes. The radius here is different. They're all different. So really your radius can be made into a function of x, because the value of x dictates what the radius is at that particular point. Okay? which we'll call r of x, is actually equal to the positive value of your y function there. Because remember, whatever your x value happens to be, that's where you're going to end up on the graph. So your radius of x is actually going to equal positive 45 over 2, 90 minus x. Okay. Any questions on that part? All right. Okay. Now, since it's a circular shape, just by description, okay, we know that your a of x is going to be pi radius with respect to x squared. You said because we don't have one set radius. The radius kind of varies. Okay, which means that your a of x is going to equal pi times your r of x squared. Okay. Oh, sorry about that. All right. Any questions on that step? All right. Okay, so we know, oops, straighten that up a little bit, that our volume, they already told us, is from 0 to 90. X equals 0, x equals 90 of pi. That radius squared, remember the square and the square root cancel each other out. So 90 minus x. Oh, yep, got to 45. Thank you. There we go. Okay,
So you.
yep, over 2.
Would be equal to the parentheses?
Hmm?
You would take that out of the parentheses?
Well, once the square root and the square cancels out, it's just there. And dx. All right. So now we can get that and we can distribute that 45 over 2. We can bring the pi out. We don't have to distribute that. So 45 times 90 divided by 2. Oh, sure. There you go. So 45 times 90 divided by 2 is 2025. Now remember, you're integrating 90, which means you have 2025x. Because the integral of a constant, you just put the x there. Okay. Minus the integral of x is x squared over 2, so you end up with 45 x squared over 2. The 2 is already there, so it's over 4. And that's from 0 to 90. Any questions on that step? All right. Okay, so now we just use our fundamental theorem. So you have 2025 times 90 minus 45 times 90 squared over 4 minus, plug in zeros, you just end up with 0 minus 0. Okay, you can just go ahead and get rid of that one. And plugging all that into a calculator, you end up with 182, 250 minus 91, 125, which is just 91, 125 pi. Or if you wanted to round it, 286,278 feet. Sorry about that. Still getting used to this. Uh-oh. There you go. All right, so once you figure out your cross-sectional area, that's when you can kind of go with the rest. But the hardest part is figuring out the cross-sectional area. Yes.
On the exam for volume, do you want to have our units cubed?
Oh, did I forget to put the cubed? Yep, I forgot to put the cubed. If you forget the cube, it's no big deal. I know what you mean. All right. Any other questions? All right. Okay, so I'll put one down and I'll let you start on it. So let's say a solid is formed by rotating the region under the curve. Y equals 1/3 square root 16 minus 4x squared about the x-axis. Okay, and x and y are in centimeters. Okay, so you want to find the volume. Alright, so what I'll do is I'll draw the shape for you, kind of get you started. Now, if you notice here, they didn't give you the x interval from this to this point. Here, you can actually figure that out. So to find your x-intercepts, just make y equals 0. Okay, so that means 1/3 square root of 16 minus 4x squared equals 0. Multiply both sides by 3, it gets rid of the 1/3. Square both sides, you end up with 16 minus 4x squared equals 0. Or 16 equals 4x squared. Divide both sides by 4. X squared equals 4. So that means x equals -2 and 2. So even if they don't give you the, I guess you say the domain or the interval, you can always figure it out. Okay, so for this one, you have -2 and 2. All right, so I'll let you kind of get started on the rest of it. Oh, one more thing. Remember, it said rotate it about the x-axis, so it looks like that.